We've looked at phase portraits before, but now we'll revisit them with a little bit more background on how these systems of equations are built, and specifically knowing about eigenvalues and eigenvectors, we're going to see how to connect those to phase portraits, and we'll see some interesting conclusions that we can draw. So here's an example to get us started. We have x prime equals this A matrix 1, 2, 3, 2 times x. I've already gone through the work of finding the eigenvalues and eigenvectors. I don't want to repeat that since we just did a few of those. So if you want to practice, you could practice going through and finding the eigenvalues and eigenvectors for this one. By the way, notice that that second eigenvector, the U2, is built a little differently than the ones we did before, where if you had picked a value of 1 for one or the other, you'd end up with a fractional answer. So what I did is I picked a value that would give us whole numbers for both of them. So you can kind of tweak it a little bit. You could play with picking a value, and then if you get a fraction, just multiply that vector by whatever value clears out the fractions. The reason I'm doing that is that I want to visualize the vector, and it's a lot easier to visualize a vector when it doesn't have fractions in it. So that's all I did there. If we draw the phase portrait for this one, again, I'm using the iPad app to do that. You'll notice, like we did before, we can draw some lines that delineate this, this phase portrait. If we draw one here and one here, more or less, there we go. That should be about right. And then notice that this one is trending away and this one is trending toward. So this is an example of a saddle point, because one of the, in one direction it looks stable and in the other direction it looks unstable. Now, if you notice, what's interesting about this is that these two lines that we've drawn are actually aligned with these vectors. So what we've been drawing so far, we haven't mentioned this because we didn't have the terminology at the time, but what we've been drawing with these lines is actually the eigenvectors of the system. So if you notice this one here, it may not be clear, but this is U2, this is the vector 2, 3, and this one down here is the vector negative 1, 1. Right, so the vector negative 1, 1 starts here, starts somewhere on here, goes to the left 1 and up 1. Right, so that would be that vector. The vector 2, 3 would start at a point and go 2 over and 3 up. So that's what we're seeing there with U2. So these lines that we're drawing are actually the eigenvectors of the system. And so knowing that, that kind of gives us a starting point for drawing a phase portrait. If you had to draw one by hand, rather than manually just drawing individual points, if you could find the eigenvectors first, you could plot them and then figure out, based on the direction that these eigenvectors are traveling, you could figure out what the rest of the field looks like. So the other question is, how would we tell that this one on this eigenvector is trending away while this one is trending toward? And that the answer to that is, if you look at the eigenvalues, you'll notice that the eigenvalue associated with U1 is negative. So here's U1. The eigenvalue associated with that is negative, so it shouldn't be too surprising when I tell you that that means it's going toward 0, right? So it's trending down toward the equilibrium. So that's a, in that sense, that would be trending toward a sink. The other one, for U2, the eigenvalue that goes with that is positive, and so it's not terribly surprising that it's going away from the equilibrium point. So that positive eigenvalue is moving away, the negative eigenvalue is moving toward the equilibrium. So with that conclusion, we can now look at a system of equations like this, and rather than trying to draw a phase portrait by hand, we could find the eigenvalues and the eigenvectors, draw the eigenvectors out, and then knowing the value of the corresponding eigenvalues, we could tell whether each eigenvector was trending toward or away from the equilibrium. And then once you know that, you can draw the whole system. So if all you gave me was this system here, if I could find these eigenvalues and eigenvectors, I could draw a picture where I say, here's one vector one eigenvector, -1, 1, and the other one looks something like this. And as soon as I know that the eigenvalue associated with -1, 1 is negative, I can tell you that's trending inward. The other one's positive, it's trending outward. And as soon as I know that, I can tell you pretty much what this field looks like. There's going to be solutions that look like this, right? So these are the solutions of the system, and it's just because of this pattern I can tell you that you're going to see this kind of X effect, and then solutions that sort of swoop toward and away from, like this, the origin. So without drawing, having a tedious process of drawing by hand, I can tell you pretty much what that phase portrait looks like if I know what the eigenvalues and eigenvectors are. And now that you know how to find eigenvalues and eigenvectors, you can answer that. And so drawing phase portraits gets a lot easier because you don't have to draw individual points by hand to get a sense of what's happening. You can get a sense of the overall behavior just by looking at the eigenvalues and the eigenvectors. So there's a summary of that on this page. The lines we've been drawing are the eigenvectors, and if there are two distinct real eigenvalues, the negative ones move toward 0 or toward the equilibrium. The positive ones move away. So if they're both positive, that means everything's moving away. That means it's a source. It's an unstable system. If they're both negative, that means everything's moving in. So it's a sink. There's a stable equilibrium. And then if there's one positive and one negative, like the one we saw here, that means we're looking at a saddle point. So that's kind of our conclusion there. And then in the next video, we're going to look at what if we have complex eigenvalues. So far we've only dealt with real ones. We're going to ask the question, what if they're complex? In that case, the solution gets a little bit complicated, I will warn you, but at the end of the day, there's basically a formula that you'll be given on the test. Because it's complicated enough, I don't think you need to bother memorizing it. And I'll let you see that in the next video.